Hello, welcome to a copy of my Automate 2023 presentation on optimizing robot paths. My name is Ilian Bonev. I'm a co-founder of Mecademic and also a full-time professor at the ETS, Montreal Engineering School. So industrial robot arms are a little bit like human arms, so they are very anisotropic. And you know, as humans, you're not going to cut tomatoes all day long like this and then put your salad bowl over here. You kind of know how to optimize the motion, how to optimize the sequence, and also there are ergonomic scientists that can help you how to do a task. But in robotics, there is nothing like this. And robots themselves, they are dumb. I mean, robots, they can hit themselves, most of them, not Mecademic ones, but most of them, unless you buy options, you can jog and they will hit themselves, so they are not aware of themselves. Also, even offline robot programming software, most of them, they don't provide optimization routines, so they will not tell you where to put your salad bowl and where to cut your tomato. They will not do this. And also, industrial robots, they offer very limited range, most of them, very limited range of possible paths, possible trajectories between two discrete robot positions. So you either have the end effector should follow a linear path or a circular path, or all the joints should follow a linear path in the joint space. So you don't have a lot of possibilities. So going from one robot position to the other, usually, like almost all of the industrial robots, they will not give you the optimized path that will be minimum cycle time. They will not do this, okay? So there is no optimization in almost all of the robots. So you need to do this optimization yourself. And even if you optimize all this arrangement of the motion of the robot position, the sequence of robot positions, there is no AI system that will give you, that will design the whole automated system for you, that will choose the best gripper, the adapter plate, the geometry of the adapter plate for the gripper, which conveyor you choose, where you place it, and so on. No system will ever do this. So industrial robots, they still need you, and they will need you for many, many more years to go. Singularities of robot arms. So when we talk about the performance of a robot arm, it's very much related to singularities. Almost all industrial robot arms, they have singularities. So what is a singularity? Very, very quickly. A singularity is a configuration where the robot end effector, not the robot itself, the robot end effector loses a degree of freedom. So this one is a 6-axis industrial robot. It has 6 degrees of freedom for displacing its end effector. But in a singularity, for example, when joint 5 is equal to 0 degrees, you lose the ability to translate the end effector in this direction. You can move this way, you can do this rotation, but you cannot go this way instantaneously. Okay, so you lose 1 degree of freedom, or maybe even more. So singularities are usually bad. They are a nuisance, but you will see today they're also kind of a gateway to workspace optimization. And all industrial robots have singularities, unless even like simple ones, like the 4-axis car here, it has a singularity when theta 3 is equal to 0 degrees. And also even this very simple Cartesian system, 6-axis system, it has a singularity when these axes, the axis of the 6th joint and the axis of the 4th joint, they coincide. So basically in this configuration, you cannot in this case, you cannot rotate about this axis. So there is no such thing as, oh, we have an industrial robot that has no singularities. This doesn't exist. What exists is that you have robots like this one and like 60, I don't know, 80% of all robot arms, they look like this, 6 axes, 1 vertical. First axis is vertical, second and third are horizontal, and then the last 3 intersect at 1 point. So this kind of very, very common architecture, it's very simple in terms of inverse kinematics. So solving the joint variables that give you the position and orientation, the desired position and orientation of the end effector. So this is called the inverse kinematics. And also the singularities are very, very simple to describe. Like you can say, oh, theta 5 equal to 0, I should avoid this. So this is very advantageous to have robots like this. But unfortunately, there are more and more industrial robot arms that have kind of fancy designs to improve reachability, to improve so that they are easier to manufacture and so on. And what people don't know about these kind of arms is that these arms, they are very complex. The kinematics is very complex. It means you can no longer say, oh, my robot is in a singularity when this axis and this coincide. No, it's kind of a very, very complicated equation. And also, there are other difficulties as well. So it's kind of difficult to say where the robot is better and where it is worse. And singularities and configurations. So configurations, these are the different solutions of the inverse kinematics. Like to go here, I can be with a right arm configuration, or I can be with a left arm configuration. So I have 2 solutions, 2 configurations. So configurations and singularities, they are very, very related. And being able to choose the configuration, like to know which configuration to choose easily, this is very important. Until one day AI will be able to do this for us. But as of today, there is no such thing. We, as robot programmers, we need to choose this to optimize the sequence of motions. So what's the problem with singularities? Like, if you, like, as I said, there are 2 different modes. You either move in Cartesian space, so you specify the path of the end effector, or you don't care about the end effector, you just move the joints kind of simultaneously, but at the same time independently. So if you move in Cartesian mode, like you want end effector to glue a line, then there is a problem. If you have a singularity, most of the robots will just stop. Or if they don't stop, and if you're very close to a singularity, they will kind of rotate some of the joints, for example, joint 4 and 6, very, very quickly, but the end effector will be very, very slow, will move very slow. So if you're doing like a gluing application, you will have a lot of glue near the singularities, which is obviously not good. In joint mode, I always tell my students, oh, you don't have problems with singularities. And that's true, but at the same time, you don't have like the robot doesn't stop, but in some cases, you still need to rotate the joints a lot. I mean, the robot will rotate them a lot. So in terms of cycle times, the motion from here to here, it's still not good. Like, again, if you're cutting tomatoes here and you want to put them here, obviously this is not optimal. So even though you have no problems with singularities, this is not optimal. So here is a demo of the singularities of the Mecha 500, but again, these are exactly the same singularities for almost any standard 6-axis robot arm. So we start with the first motion, which is close, which is actually inside wrist singularity. So this kind of rotation, you don't get it in industry. Nobody will do it. It's just to illustrate that my degree of freedom of the end effector, I lose 1 degree of freedom at the end effector, but I gain one completely useless degree of freedom inside the robot, self-motion. So just to show where this degree of freedom goes, it goes to something which is completely useless. So nobody will do this just for show. So this is to show we lose this degree of freedom. We gain it as self-motion. But normally, most industrial robots, if they get into this configuration, they will simply stop. And here, when you pass close to this singularity, what happens? It's the robot slows down. So I ask the robot to follow a line with a constant speed, but it cannot, because to do this, joints 4 and 6, they should rotate more than the maximum velocity of the motors 3 and 4 and 6. So it cannot, and it will slow down so that it can rotate fast enough while keeping the linear path. So this is what happens when you pass close to a wrist singularity. Then, well, let's watch it again. So wrist singularity, then you have what is called the elbow singularity, actually a shoulder singularity, which is kind of similar, but more difficult to calculate. So again, it's going slower. So you don't do a gluing application here, a singularity. Okay, this is the elbow singularity. This is kind of very simple. The elbow singularity is like, okay, you cannot go farther. So this kind of motion I'm doing here is just to show that even though I'm moving some joints, well, the end effector is almost not moving. So obviously, if you want to go fast, you don't do anything here. You do it here, right? So this is the elbow singularity, kind of very, very easy to avoid. And here is the other singularity, which is much more kind of complex. Again, this motion, very, very difficult to program. You need to be a specialist on inverse kinematics. So nobody will see this in real life. But I'm just showing it to show that we lose 1 degree of freedom at the end effector, but we gain 1 useless degree of freedom in the robot itself. And when you pass close to this singularity, you have a very, very dangerous motion. In the case of the Mecha 500, it is not dangerous, but imagine if you have a large robot, it will slow down, the end effector will be very slow, but the base will rotate very fast, which is very dangerous, especially in collaborative robots. So you need to be able to avoid this kind of singularities. So singularities and configurations, as I said, these are related. So the singularities, wrist singularity, shoulder singularity, elbow singularity, 3 types of singularity in a typical 6-axis robot. They separate what we call the configurations, which are basically in this type of robot architecture. We have 8 different solutions to the inverse kinematics, and these 8 different solutions are obtained by multiplying 2 possibilities times 2 possibilities times 2. And these 2, 2, 2, they are called flip, no flip, basically theta 5 equal positive or negative. Some kind of angle, sometimes it's 0 degrees, sometimes it's 90 degrees, whatever, it's a constant value. So when this angle is less than this value, it's like elbow down, otherwise it's elbow up. Basically the center of the wrist, which is really like where the 3 axes, the last 3 joints, where they intersect, when this point is in the plane of axis 2 and 3, there we have the singularity. And the shoulder singularity in this architecture is when the center of the wrist is on line on the axis 1. So if we call front and back, but it's not with respect to the base of the robot, it's with respect to this kind of plane that passes through joint 1 and joint 2. So if the center of the wrist is in front of this plane or rear this plane, so we have the other 2 possibilities. So this is the 3rd parameter, configuration parameter. So most robots will let you choose the configuration you want by using these 3 binary parameters. And to be able to switch from one configuration to the other, you will need to cross a singularity, which means that typically you need to switch to joint mode in order to do this kind of motion. Not always, we can do it, and I'll show you, but most robots, you need, if you're jogging, you need to switch to joint mode in order to be able to switch from elbow down to elbow up. So again, a singularity, you lose a degree of freedom of the end effector. You gain it, the lost degree of freedom, you gain it as a useless self-motion. Well, in this case, you don't gain it. It's really like you don't gain anything. It's the end of the workspace. And singularities, again, they separate the, usually, again, for the normal architectures, singularities separate the different inverse kinematic solutions. And this is good because it means that if you fix a configuration, you will never be able to suddenly go to another configuration. But there exists industrial robots in industry that they don't have, they have a default, let's say they have some very, very bad characteristics, which means that you can start a motion and then repeat some sequence, and at the end, you will think that you're in the same configuration, but actually the robot is like this. So this is very dangerous. Most robots are not like this, but there exists at least one such industrial robot arm on the market that is like this, and this is dangerous. So the inverse kinematics, okay, why do we care about the inverse kinematic solutions? Because the workspace of the robot, we care about the workspace of the robot. And many customers, they ask us, oh, well, what's the reach of the robot? Why do you care about the reach of the robot? The reach of the robot is like only to choose between like a big robot and a small. But if Mecademic only has one robot, it doesn't matter that I give you a number, it's 254 centimeters or something like that, millimeters. It's the reach is just the distance between the maximum distance between the center of the wrist and axis 1. So this is not the workspace. This gives you some idea of how big is the robot. Maybe for the SCARA it gives you a good idea, but for a 6-axis robot it doesn't give you anything because this is just a single number. The workspace of a 6-axis industrial robot is actually a set of 8 different subsets, and each subset corresponds to one of the configurations of the 8 possible configurations. And actually it's even more because some of the joints, they can rotate. So you can be at 1 degree or you can be at 361 degree. Like mathematically this is the same, but physically if you have cables it's not the same. So sometimes if you are at 1 degree, you want to go to -1 degree, this is good, it's acceptable, but sometimes it's not acceptable. So if you add this, you even get more than 8 subsets, but let's stick with 8 subsets. So because of joint limits, obviously I can do like this, but I cannot do a lot in this configuration, elbow down. So because of joint limits, which are not symmetric, in some of these subsets, I can reach some poses. The end effector can reach some poses, but in other configuration, I cannot reach them. So maybe if I want to go like this, well, there is only one possible configuration that I need to choose in order to be able to go there. So you need to be aware of this, because like when my students jog to teach the robot to go somewhere, they forget it and they always stay in Cartesian mode. But if you stay in Cartesian mode, it means you can never cross a singularity. So if you can never cross a singularity, it means you can never change the configuration. So you're stuck in only one of these 8 subsets. These 8 subsets are the subsets of X, Y, Z, and then the 3 orientation parameters, Euler angles, let's say, that represent the orientation of the end effector with respect to the base. So for the same pose of the end effector. You can have different configurations. So physically, it's the same XYZ you'll pitch row, but it's actually 8 different subsets, because from one subset you cannot jump to the other if you stick in Cartesian mode. You need to switch to joint mode or be able to cross singularities. So let's see the same thing in the case of a scalar robot, because it's much simpler to see. So this is your scalar, the workspace of a scalar robot. And if you decide to use it only in right mode for whatever reason, well, you can go only in the part that is hatched like this. If you wanna, this is the right mode actually. In the righty mode, you can go this part, but you cannot come here. You can come here, which is useless, but you cannot come here. So if you want to go from here to here, there is no way to go to do this in following a line, for example. There's no way. The only way to go from here to here is in joint mode, for example. But if you absolutely need to pick something here and put it back here, then it seems very close. So it seems like, oh, I'm here and then I need to put it here. But actually, I will have to make a very big motion to come to here. So this is very important, because people think, oh, this is my workspace. Everything here is my workspace. But no, it's 2 workspaces kind of superimposed. So you need to be careful how you go from one place to the other, where you put your conveyors, etc. So in the case of a scalar robot, we only have 2 configuration modes, and we have 2 subsets which are kind of superimposed. Easy to understand. And the singularity is very simple. In this case, it's the blue curve. It's the frontier, the boundary of the workspace. But like oftentimes we say singularities are the boundary of the workspace. But that's wrong. Like, it's the boundary of the workspace, maybe the elbow singularity, because it's really, you cannot go further. But in the other case, it's not really the boundary. It's basically kind of a wormhole, like a passage from one subset to the other. And this passage is not a boundary. It's just that instead of being 6-dimensional, it's 5-dimensional. So you lose some degree of freedom, but you still have 5 degrees of freedom to cross this singularity. So there is no problem. Like, you can do it. Mathematically, there is a problem, but physically, there is no problem. You can do it. So let's say in this type of scalar robots, which are called orbital design, which have the link 1 equal to link 2, and then you can go there, and manufacturers of these robots, they say, oh, you have a big workspace, you have no hole inside, so you can go everywhere, which is true and not true. Okay, that's true. You can go and pick something anywhere. So yeah, your workspace is a complete circle. But let's say I ask you to move along a line that crosses the center of the circle. Well, you cannot, because you will have to cross singularity when this axis, the axis of the spline shaft, is coincident with axis 1. So basically, in this case, you can move the scalar robot like this, and the end effector doesn't move at all. It's useless. So again, the first subset, blue, when the robot is with the right-hand configuration, green when it's with left-hand configuration. But if you want to move along a line, then it is a hole. There is a hole in the workspace. It's kind of a wormhole, but it's a hole. So you can do it physically, but if you do it on most industrial robots, the robot will stop. You cannot do a line. And okay, somebody will say, well, with scalar robots, we don't follow lines, we just do pick and place in joint mode. It's the same. I will show you, it's not optimal. So even though you think, oh, I'm here, I need to go here, it's very close, it's inside the workspace, it will take you a lot of time. So it's not an optimal trajectory. Same here. If my robot is like this, there is nothing physical that prohibits me to go from here to here and cross this singularity? There's nothing. Mathematically, there is a problem, but I can do this, and by doing this, I can switch assembly modes, which is working modes. I can go from one of my subsets to the other without, crossing a singularity by precisely, crossing this small crevice, which is the singularity. And by doing this, I can do a very long line. So my workspace is now bigger. So maybe this is not an optimal motion for pick and place, but if somebody is using the Meca 500 for testing whatever, something, and they just need 5 millimeters more or 5 centimeters more, well, by doing this kind of trick, they can do it. Otherwise, if they stick to one of the subsets, they will never be able to do it. So this is very, very interesting. Here is again an example with this orbital type of scalar robot. So let's say, okay, you don't cross the singularity, you're just very, very close to this singularity. So what happens is there's nothing to do. The robot will need to rotate very fast. So this is not optimal. This is not optimal. So what do you do in practice to improve this? Well, number one is just move the path away, move it farther. So if you do this, then you see joint one must rotate maybe 90 degrees and joint two almost doesn't rotate. So this is kind of optimal. Another solution that many manufacturers offer, they call it singularity avoidance, but basically is you ask the robot to follow a line, and then the robot doesn't follow a line. So it's kind of an avoidance, but it's you no longer follow the line. So if you are gluing, you cannot use this approach. Maybe if you are just removing something like moving away from a table, it's okay, but otherwise this is not really feasible approach. And then the other approach, which we're not the only ones at Mecademic. There are a couple of companies who do this, but it's definitely not most of them, most of the robot manufacturers. So the other approach is just be able to change the configuration, cross the singularity, and then you can do this, which I haven't studied in this example, but it kind of seems this is the optimal motion, better than this one, because I need to rotate less. Joint one, which is like the heaviest to rotate, the most difficult, the inertia, everything. So joint one rotates a little, joint two rotates more, but then joint two is kind of easier to rotate. So it kind of seems that this is an optimal solution for the path placement in this case. So here is again, here is the demonstration of this crossing of a singularity. It's kind of fast, but you will see I start from a singularity and I can go all the way from here to here, basically passing two singularities. So crossing one workspace set, another, and then another. So with the same path, I'm able now to test whatever my VR glasses. Okay, now I'm able to test them at this distance and at this distance and at this distance using the same robot. I don't need a bigger robot. I don't need a linear stage, and I can do this just because I'm able to cross singularities. Of course, you need to know how to do this. You need to know where to start and where to go, because if you go just 1 micrometer away from this path, you will not be able to do it. So you need to enter the right numbers. You need to program this manually, not using like a joystick or hand guiding. So you need to do this with exact numbers. But if you know what you're doing, then you get more out of your workspace. So I was talking about crossing singularities, but there is also the choice of configuration. Now there is a very good video on YouTube from Fanuc who explain like, okay, you have a conveyor, you have a robot, and you have to pick stuff based on a camera. And what do you do if you run into singularities from time to time? And the solution, the best solution, of course, is to what they propose is to put the robot on a riser, or maybe change the adapter plate for the gripper, or maybe move a little bit the robot and then try. And this is definitely the best way, even though it's trial and error. But if you are stuck with this installation and you cannot move your robot, well, another thing you can do is simply go there with a different configuration. So for example, you have to go there, but it's a singularity. So you just go to this configuration. Maybe it's not optimal, maybe it will take you more time to go there, but at least you don't have to change the whole setup. Ideally, you should not be doing this, but this is a possibility. And sometimes actually it's ideal to do this, because you can reach, with a small robot, you can reach some poses which otherwise you will need to have a much bigger robot. So again, when you never, that's what I don't like about hand guiding. And we have collaborative robots in my lab at ETS, and I don't like students to use the collaborative mode, the hand guiding mode, because when you're hand guiding, you are always kind of, you can change everything, but it's kind of a puzzle. You need to know how to do it. But the best way is to use, in the case of ABB, because we use ABB robots at DTS, you use the Robot Studio, basically the robot software, simulation software. And the best thing is to always use the robot software, robot simulation software, because you can easily choose like the best configuration by visualizing, by going there in some configurations menu. And this is the best way, because if you do this by jogging on the real robot, you will probably never think of going somewhere in some kind of fancy configuration. So always use robot simulation software. It can be RoboDK, for example. In the case of Mecademic robots, you can use RoboDK, you can use other robot software, but use simulation software, because again, when you're jogging, you don't see this. And if you're hand guiding, you even see less of it. And unless you're very, very well acquainted with the robot, hand guiding, it's very suboptimal. It's easy. If it works, it's easy. If you're doing some simple machine learning, it's perfect. But if you want to do something optimal, hand guiding, it's not the best solution. So I talked about changing the adapter plate. Of course, it's very, very important. The configuration of everything. It's not just the robot. And again, the workspace. What is the workspace of your robot? I don't know. What is the end effector you're going to use? Because I don't care about the workspace of the robot. I care about the workspace of the end effector, the set of poses attainable by the end effector. So how you attach your end effector to the robot is extremely important. You want more reach? Well, just put a very, very big adapter plate. You can go farther, but you will not be able to rotate a lot. So there is no science. I mean, well, there is, like my master students sometimes will do like optimization using genetic algorithms to find the optimal placement of the end effector and everything else in the cell. But you don't have this usually in robot software, and it's kind of difficult. So at least you should know that it's very, very important what kind of adapter plate you use, what kind of end effector you use, what kind of cable you use. It changes your workspace. It restrains the joint limits. The singularities will be completely different. So this is very important. Also in the case of axisymmetric tools like gluing or welding or machining, you have this redundancy. And so use it wisely, because using this redundancy, which is the orientation about the axis of symmetry of the tool, you can use this to avoid singularities. And I've heard this many times, oh, the best angle is 45 degrees or 30 degrees. There's no such thing. Like I've never seen a scientific paper prove that this is 30 degrees or 45. Play with it. it can be 15 degrees maybe. It depends on the robot. Like our robot is very special because it has quite long links here compared to the robot itself, but maybe on other robots it will be different. So there is no such thing as 30 or 45 degrees, but definitely not, don't align it with the axis 6, because you're basically wasting 1 degree of freedom. And something I'm sure most people, they don't know, but like when I started teaching like 20 years ago, I was like, oh, usually you put the z-axis along the tool. This is wrong. This is totally wrong. You don't put the z-axis along the tool axis, because, and I'll tell you why. Like if you have cooker robots or ABB robots, for example, the Euler angle convention is rotation about z-axis followed by rotation about the tool y-axis followed by rotation about the tool x-axis. So if you want to be able to easily change the rotation about the tool axis, put the x-axis there, which is the final rotation. So by changing only one Euler angle, not all three of them, only one of them, you will be able to try like different rotations. And by doing this, you can avoid singularities. In case of Stobie robots, in case of Mecademic robots, we use a different Euler angle convention where the final orientation is about the z-axis. So you place the z-axis along the tool, along the axis of the tool, and then you can easily, just by changing the gamma angle, you can easily obtain a different configuration, which is maybe away from a singularity. So this is something very useful to know. Another thing to avoid singularities and also extend your workspace, improve your cycle times, is use a linear guide or a rotary stage. So you only add a fraction of the cost of another robot or a bigger robot. And by doing this, ideally, they should be synchronized so that you can do kind of a synchronous motion with both units, the robot and the external axis. But even if they are not, it's still very, very useful. And you can, again, if you design the whole system correctly, you can have a much larger workspace without singularities, or actually avoid singularities, because you have redundancy. So now, not only you have the 8 different configurations to choose among, but you also have infinitely, 8 times infinity configurations to reach a desired pose of the end effector with respect to the base frame. So this is something, another solution. And then again, I started this and I will repeat it at the end. Simplicity is very important. So I don't want to trash talk about industrial robots, but I'm also a researcher, so it's kind of difficult. No, most collaborative robots, like universal robots, they seem like a very, very special architecture, but it's actually a very, very good architecture, which has analytic solution of the inverse kinematics, and the singularities. They're kind of different from the singularities of this type of robots, but they're also very, very simple to explain. I have a paper on this, and also on the tutorial on the Mecademic website, we explain the configurations. So they're very, very similar. So it's kind of simple to, it's not symmetric, but it's simple to know, okay, this is a singularity, this is flip, no flip, etc. But there are more and more architectures which, well, sometimes you have no choice. Like if you have painting robots, they always have what we call not inline wrist, basically wrist where the 3 axes, they don't intersect. And this is simply because with this kind of wrist, you have a very small, well, not that small, but small range of motion for θ5. But for painting, you need to be able to get inside the body of the car and do this kind of motion. So you cannot do it with this kind of wrist. So that's why for some applications, it's necessary. You need to have this kind of wrist. But for other applications, I know they kind of optimize the robot to make it able to rotate more and so on. But the thing about doing this is the robot becomes very complicated in terms of kinematics. So now the user, well, let me give you one example. You go to RoboDK, and a robot that has complex kinematics, first thing you notice, well, they don't give you all the configurations. Why they don't give you all the configurations? Because they don't know how to calculate them, because they don't have like 3 or 4 months to spend on doing research in order to be able to, give you all the different solutions. So first thing, if you have this kind of special architecture, you cannot use software like RoboDK. Also, if you no longer know where the robot is in a singularity, so you kind of move and then suddenly it stops and okay, it's a singularity. I didn't know. So why is it in singularity? You don't know. Like you cannot say, when axis 1 and 2 are parallel or something like this. You don't know. It's very, very complex. And again, some of these robots, you can start from one robot position and then move to the same robot pose without crossing a singularity, which is dangerous because basically there is no way of specifying to the robot, I want you to visit this end effector pose always with the same robot configuration. So this is kind of dangerous. So there is the robot architecture of a 6-axis robot, the way the 6 axes are arranged, one with respect to the other. But then there is also the 7-axis robots. 7-axis robots, previously they used to be like reserved for the Canada arm, for space applications, for research applications. Now there are a lot of companies making 7-axis robots, and many of these are really great. Like there are definitely advantages of using 7-axis robot. You can avoid obstacles, and also I thought you can avoid singularities by using this redundant degree of freedom. But then when we bought a bunch of 7-axis robots for my lab, teaching lab, I discovered that you can avoid singularities, but you actually have more singularities. So more that basically you can write a scientific paper about this. So again, very good robots, but you definitely need even more expertise on singularities to be able to work with these robots. And then again, people will say, you can use artificial intelligence to decide which is the best configuration, and you don't need to worry about this. Okay, where is it today? Because today, all the robots that I use in my lab, none of them has artificial intelligence. And even if I jog in linear mode from one position to the other, this redundant motion can be optimized, but it's not. So one day maybe I don't need to worry about all this, but as of today, there is no intelligence in most of these robotic arms. So I need to optimize this. I need to avoid singularities. The robot will just say, it's a singularity, I stop. So I need to place everything in my robot cell so that I don't have singularities, I don't pass through singularities. So again, unless you deal with a very simple pick and place application like machine tending, 2-3 different picks and places, you definitely need to learn about singularities. It's not, I know I'm a researcher and I like them and this is my topic of research, but it's really, if you don't know this, your application will be slow, or maybe it will not even work from time to time. And again, the optimal placement, there is, and probably there is some software here and there that can do some kind of optimization. But for now, most people should just be aware then they should do a lot of trial and error. There's no other way currently, like the typical way, unless you probably pay thousands and thousands of dollars, and I've never tried it, but most robot simulation software, even if it costs thousands of dollars, they don't do this kind of optimization. They don't tell you, to do this line, you better do it here rather than here. Or to do this application, you'd better use the 90-degree adapter plate from Mecademic rather than the flat one. There's no software that does this now. And optimal choice of configuration, again, sometimes if you use specific commands, the robot will go to the best configuration automatically. So sometimes this is taken into account, but if you really want to go there in linear mode or in some specific applications, then you need to specify the desired configuration. You cannot leave the robot to decide it. And again, the design of the end effector, how you attach the end effector, how you design the whole system, it's very important. And you should always start with this. And you should do these two concurrently. Not first buy the gripper, put the gripper, and then try to design everything, and then, oh, my robot is too small. Mecademic, do you have a bigger robot? No, we don't. But maybe if you just redesign your cell, then you will be able to do this task. Oh, I want to do very, very long motion for my virtual reality test. Well, no problem. You just cross a singularity, and then you will be able to do a very long motion. You don't need to buy a bigger one, bigger robot. So this is most of the things you need to know about singularities, about path optimization. It's not enough, but it's just to give you an idea of what's out there. And again, I have a tutorial on robot singularities with some videos and so on. It's on the Mecademic robot website. And thanks again to Automate for inviting me to give this talk in Detroit. And I'll see you next year in Chicago. Thank you.